Welcome. We are now approaching the end of module 2, that is flow sheet synthesis. So far we have seen various aspects of flow sheet synthesis, various levels of flow sheet synthesis, the decisions that we have to make at each stage, and thereafter we also dealt with a few problems on the selectivity in parallel reactions as well as series reactions. Now, in this lecture, which is the second tutorial of this module, we shall deal with the selectivity in multiple reactions which are neither necessarily parallel or series, and we shall also see some problems on synthesizing a flow sheet and determination of the economic potential of the flow sheet at various stages. So, we start with the first problem, that is the selectivity determination in multiple reactions. Now, let us see the problem statement first. Consider the reactions A plus B goes to C with rate constant K1 and A plus C goes to D with rate constant K2. Now, C is the desired product and D is the undesired or waste product. Now, these reactions are carried out in CSTR at 10 degrees centigrade and 6 bar pressure. Okay. The flow rate of the reactant A and B is Q, unit may be meter cube per second, and the volume of the reactor is V meter cube. Okay. Now, we have to determine the selectivity in terms of conversion of the limiting reactant A. Determine the selectivity in terms of conversion of limiting reactant A. The molar ratio of the reactants, the initial molar ratio at the point of entry, you can take as B naught by A naught, and this molar ratio is indicated by letter M. The time constant or the residence time of the reactants will be equal to the volume of the reactor divided by the volumetric flow rate. We already know that molar ratio is B naught by A naught, and now what we do is that we denote the moles of the 4 component of the system by the same letter. A, B, C and D. Now, at any time t greater than 0, the net change of moles of A, which is A naught minus A, would be equal to tau into K1, the rate constant, into A and B, okay, and plus K2 into A into C. Similarly, B naught minus B, the change of number of moles of B would be equal to tau into K1 into A into B. Okay. And the number of moles of the 2 products formed, C and D, will be, for C it will be tau into K1 into A into B minus K2 to A into C, and for D it will be tau into K2 to A into C. The selectivity S will be equal to C, the desired product, divided by the limiting product converted, A naught minus A. We substitute for C as well as changes in the other excess component B, C divided by B naught minus B, and then we get, for C we substitute the expression that we just wrote, K1 into A into B minus K2 into A into C divided by K1 to A into B, and thus we get the expression 1 minus capital K into C by B, where capital K is the ratio of the rate constants of the two reactions. We make this expression explicit in terms of C. You can simply rearrange the equation, which is rather straightforward. C into 1 plus capital K into B naught minus B by B divided is equal to B naught minus B, and thus C is equal to B naught minus B divided by 1 plus K into B naught minus B by B. So, this is our first result. We can also write that number of moles of C formed are the number of moles of B reacted minus the number of moles of A reacted, okay, based on material balance. And then we get A naught minus A is equal to B naught minus B minus C, and now for C we substitute the expression that we just derived, A naught minus A is equal to, now B naught minus B is the number of moles of B converted. So, we can write that in terms of the conversion of B, XB is the conversion of B, B naught into XB, minus for C we write the expression that we just derived, B naught into XB divided by 1 plus K into XB divided by 1 minus XB. Now, what I have done here is that I have converted the expression for C in terms of conversion for B. Now, that is rather straightforward, that I show now. XB is equal to B naught minus B divided by B naught. Therefore, B is equal to B naught into 1 minus XB, and therefore, C is B naught into XB divided by 1 plus K into XB divided by 1 minus XB. So, this is the essentially the transformed form of what we wrote earlier, that C was equal to B naught minus B divided by 1 plus K into B naught minus B divided by B naught. So, what we have done, the previous expression we have transformed into in the form of the conversion of B, XB. Okay. Now, we go further with this, the expression that we derived earlier. A naught minus A was B naught into XB minus B naught into XB divided by 1 plus K into XB divided by 1 minus XB. That we now rearrange. A naught minus A is equal to B naught into XB into 1 plus K into XB divided by 1 minus XB minus 1 divided by 1 plus K into XB and 1 minus XB. And this we can further simplify as B naught into XB divided by into k into xb divided by 1 minus xb whole divided by 1 plus k into xb divided by 1 minus x. A naught minus a itself can be written in terms of conversion of. Define xa, the conversion of a, the limiting reactant, as a naught minus a divided by a naught. So, a naught minus a is essentially a naught into x a, and that we substitute in the previous expression. A naught x a, which is equal to a naught minus a, is equal to b naught into x b into k into x b divided by 1 minus x b whole thing divided by 1 plus k into x b divided by 1 minus x b. So, what we have now is x a as function of x b. We further arrange this. X a is equal to b naught by a naught by taking a naught here on this side into x b, and we simplify now this square bracket as k into x b divided by 1 minus x b plus k into x b, and this becomes b naught by a naught is the molar ratio m. So, that we substitute m is into x b into k x b divided by 1 plus x b into k minus 1. And now, if you expand this, you get a quadratic in terms of x a, in terms of x b, which if you solve will give you an explicit expression for x b as function of x a. This I leave as exercise. It is simple. I will give the final form of quadratic which you can solve. Mk into xb square is equal to xa into 1 plus xb into k minus 1. This is what you get if you expand that the previous equation, which you can rearrange in the form of our regular quadratic equation ax square plus bx plus c this is of the form, and then you know that the roots are minus b plus or minus b square minus 4ac by 2a. So, here you have a as mk. Now, a, b, c are not here, do not confuse a, b, c with number of moles, but these are simple coefficients. So, a is mk, b is k minus 1 and c is minus xa. So, if you simply substitute these three things in this equation, the simple root, you will get the desired answer, that is x b as function of x a. And now, this I have left as an exercise. Okay. We can come back to the selectivity. Okay. Selectivity we have defined as the number of moles of desired product C formed divided by the number of moles of A, which is a limiting reactant converted. So, C divided by A naught minus A. And now, if we substitute the two things, we already have expression for C and A naught minus A in terms of x b. So, if you substitute that, substituting for C and A naught minus A in terms of x b, will give you the following. S will be equal to C, which we have obtained as B naught into XB divided by 1 plus K into XB divided by 1 minus XB, and for A naught minus A we obtained B naught into XB and K into XB divided by 1 minus XB, whole thing divided by 1 plus K into XB divided by 1 minus XB. Okay. And this can be simplified as 1 minus XB divided by KXB. So, we have selectivity in terms of the conversion of B, and if you substitute for B XB in terms of XA by solving the quadratic equation that I gave earlier, you will get the desired answer. So, that final answer I have left as an exercise for you. So, this is how you determine the selectivity in case of multiple reactions, which are not necessarily parallel reactions or series reactions. Okay. So, we have dealt with all three types of selectivities. Okay. We go to the next problem. In this problem, we have to determine the economic potential of a particular process. But before that, we have to do the material balance, and then we have to do some initial calculations. Okay. So, let us try to do that first before we go to economic potential. The problem statement is on the screen. What we have is an energy integrated process for producing acetone from isopropanol. The flow sheet is on your screen. This is what is the flow sheet. You have the feed is the isopropanol azeotrope IPH2O feed, which first goes into a preheater, then it goes into another exchanger, that is FEHE, feed to effluent heat exchanger, then it goes to the reactor. Since it is endothermic process, you have to supply heat which is given by a furnace, and the reactor effluent initially passes through the same feed. We shall see the second problem of this tutorial, that is the flow sheet synthesis for the acetone process. Acetone is manufactured by dehydration of isopropanol, and we have the basic reaction as isopropanol getting decomposed to acetone and hydrogen. Okay. Now, let us see the basic aspects of this particular. The feed of the process is an azeotrope containing 70 mole % of isopropanol. The reaction takes place in a CSTR, where the heat is supplied for the reaction. Since this is a decomposition reaction, it is an endothermic reaction, and the heat of reaction is plus 25,800 BTU per mole. The heat capacity of azeotrope is 22 BTU per mole per degrees Fahrenheit. The reactor conversion is 80%, and the inlet temperature of the feed is 572 degrees Fahrenheit. Okay. Now, you can easily convert these units into SI system by 1 BTU is 1.055 joules. You already know the conversion between degrees Fahrenheit and degrees centigrade. Okay. Degrees Fahrenheit is 1.8 times degrees centigrade plus 32. Okay. So, this simple conversions we can do. Okay. The heat for the reaction is supplied by condensing a Doutham liquid in the reactor shell. The reactor is essentially a shell and tube heat exchanger in which the tubes are packed with the catalyst and the reactant isopropanol flows in the form of vapor over the catalyst, and the heat is supplied by condensing a Doutham liquid, vapors of Doutham liquid into the shell of that particular heat exchanger. The temperature of condensation of the Doutham liquid is 600 degrees Fahrenheit. The Doutham liquid is vaporized in a furnace which is attached to the reactor, okay, and the thermal efficiency of this particular furnace is 60%. Then as the vapors of Doutham pass transferred from the furnace to the reactor, the heat losses in the pipes or the transport lines are about 20%. So, you can say the heat loss is about so that heat loss is about 20%. Okay, that is it. The fuel cost of the furnace, which could be an oil fired furnace or diesel fire furnace, okay, can be taken as rupees 500 per MMBTU, million metric tons BTU, okay, and the process operates 8,000 hours a year. So, this is the data that we have for this particular process. We have to answer following questions for the process. First, draw the input-output structure of the flow sheet. Next, determine the flow rates of all components at inlet and outlet of the process. Third is draw the recycle structure of flow sheet. And determine the recycle material balance. Then the next is determine the annual cost of fuel for the furnace. And finally, determine the area for the reactor. I told you that the reactor in the present case is in the form of shell and tube heat exchanger. So, we have to determine the area of this heat exchanger. let us start dealing with these questions one by one. The first question, that is the input output structure of the flow sheet. Okay. Since we have only one reaction in this particular process, the structure is relatively simple. We have a process in which there is only one feed stream, that is the isopropanol water azeotrope, and then there are three products. First is the main product acetone, then hydrogen, and some water will come out. Now, how we shall see in few minutes. Okay. Let us say we have not been given the production rate of acetone. So, we assume a simple rate, production rate of acetone PA as 100 mole per hour. If you see the stoichiometry of the reaction, then the production rate of hydrogen will also be 100 mole per hour. The fresh IPA feed will also be 100 mole per hour. I hope you recall that at steady state all the fresh reactant gets converted. So, if you see the stoichiometry, 1 mole of acetone requires 1 mole of isopropanol. So, the fresh isopropanol feed will be 100 mole per hour. All of these determined by stoichiometry. The feed is not pure isopropanol, but an azeotrope. So, the amount of water that enters with the feed will be 0.7 into 100 divided by W plus 100, where W is the total moles of the feed. So, W becomes 42.9. The total azeotrope will be 100 mole per hour of isopropanol plus the accompanying water, which is 42.9 mole per hour. So, total 142.9 mole per hour. So, this is what will be at the inlet. Okay. So, we have determined all flow rates of all components at the inlet and outlet of the reactor. We summarize: isopropanol water azeotrope 142.9 mole per hour, acetone 100 mole per hour, H2O 100 mole per hour. Now, we have not still yet determined the amount of water. Now, that we shall do now. Out of this azeotrope, the isopropanol gets converted and water is left out. Okay. That water will be 42.9 mole per hour. So, if we compare this particular process to the HDA process that we have seen, water you can consider as an impurity, and then that has to be removed from the process at all time. Therefore, the flow rate of water at reactor outlet will be equal to 42.9 mole per hour. Therefore, we write this parameter in the flow sheet: H2O 42.9 mole per hour, and therefore, we have determined the complete input output structure of the flow sheet with the material balance. Let us see the recycle structure of the flow sheet. The per pass conversion in the reactor is 80%. Okay. Therefore, there will be IPA unconverted. Now, that IPA will contain excess water, which is this 42.9 mole per hour. Before recycling, we have to remove this water. So, the outlet of the reactor effluent should pass through at least 2 distillation columns. In the first column, the main product acetone will be removed from IPA, and in the second column, excess water will be removed from IPA. So, in that column, the main product will be IPA azeotrope, which will be recycled back at the reactor inlet, and it will be mixed with the fresh azeotrope feed. Okay. So, that point we note that the separation system of the process should contain 2 distillation columns. First column removing the main product acetone, and second column removing excess water from IPA to distill off IPA azeotrope, which will be recycled at the reactor inlet. Okay. So, now we can very easily draw the recycle structure of this particular flow sheet. We have first the process or the reactor. Okay. The feed to the reactor will be the fresh IPA azeotrope. Then the reactor effluent should enter a separation system. Product hydrogen can be taken out because it is not a reversible byproduct. Okay, so hydrogen can simply leave the separation system and can be used elsewhere. The 2 products acetone and water and leave the separation system, and there will be one recycle stream containing IP azeotrope, which will be mixed with the fresh feed. Okay. So, this is a simple recycle structure of the flow sheet. We have determined it from theoretical considerations. We have to determine the recycle material balance. Okay. The total IPA feed, which is at the reactor inlet, which is the mixture of the fresh and recycled feed. So, the total IPA feed we denote as FIPA. FIPA is equal to the fresh feed IPA, that we denote as FIPA divided by the conversion. Now, this is a relation that we have used earlier in case of HDA process as well. So, this directly applies in the present case. Okay. Then we can easily, if we substitute all the values that we have, FIPA, the total feed of IPA should be 100 divided by 0.8, which is a per pass conversion, and that is 125 mole per hour. The IPA in recycle stream it will be obviously the unconverted IPA. We have assumed complete recovery of IPA, no losses. So, IPA, F IPA into 1 minus x. So, 125 into 1 minus 0.8, that turns out to be 25 mole per hour. I write here the assumption that we make complete IPA recovery with no losses. Now, this is the amount of isopropyl alcohol in the recycle stream, but the recycle stream is not pure isopropyl alcohol, but an azeotrope. So, there will be definitely some water accompanying this particular IPA. Now, we assume that in that second distillation column, we can distill off IPA to the azeotrope level, that is up to 70% of IPA. So, then H2O in recycle stream. Here also we write the assumption that the second distillation column distills off 70% IP azeotrope. Okay. With this assumption, we can say that the amount of water in the recycle stream will be 0.3 by 0.7, that is 10.7 mole per hour. So, now we have determined the amount of the material balance of the recycle stream. Okay. So, the total recycle stream will be 25 plus 10.7, that is 35.7 mole per hour. So, that point we note here, 35.7 mole per hour of the recycle stream. Now, the third question was about the reactor heat effect. The reaction is endothermic reaction, and then we have to supply the heat of reaction. Assuming that the reactor operates isothermally, which means that the temperature of feed and effluent from the reactor is same, we can easily calculate the amount of heat that is required. Okay. Are given the temperature of feed as 572 degrees Fahrenheit. Therefore, the net heat load will be 25,800 into 100. This is BTU per mole and 100 mole per hour of reaction. So, this is 25,800 BTU per hour. So, this is the reactor heat load. We are given the temperature of feed as 572. We assume isothermal operation, that means the temperature is same at the reactor inlet and outlet, and the Dow-therm vapor condenses at 600 degrees Fahrenheit. This was also given to us. If we assume no subcooling of the condensate, the driving force or delta T will be 600 minus 572, that is 28 degrees Fahrenheit. Now, we have not been given the overall heat transfer coefficient. If we have to use the relation Q is equal to UA delta T, okay, we do not know right now the U. However, if we have a vapor system, okay, that means in a shell and tube heat exchanger, let us say one pass each, one shell pass and one tube pass, and vapor is reaction in vapor phase is occurring in the tubes, and there is heat transfer, a vapor condensing in the shell. The typical heat transfer coefficient that you are likely to have is something like 10 BTU per feet square per hour per degrees Fahrenheit. Now, this value I have obtained from the order of magnitude heat transfer coefficients given in standard texts, like for example, Perry's handbook, or the book of Holman heat transfer, or the book of DQ Kern process heat transfer. So, for these kind of systems, a typical heat transfer coefficient is given, and I have taken the value of U from this text. Okay. Substituting now all the values that we have, area is equal to Q divided by U delta T. Q we have just determined as $2.558 million BTU per hour, U is 10 and delta T is 28. We get the total heat transfer surface as 9214 feet square. So, that answers our fourth question. And then the last question, the annual fuel cost. From this area, you can also get the cost of the heat exchanger reactor, but that point we are going to deal in the other module of process economics, in which we shall see the cost correlations. So, that point I defer for the next module. Annual fuel cost, okay, we have to determine now. The Tautham liquid is evaporated in a furnace, and those vapors are transported to the reactor, and then the vapors condense in the shell. Okay. So, there is, in the first place, the furnace efficiency comes into picture, and then the heat losses. We have been given furnace efficiency as 60%, heat losses as 20%. Okay. So, and the fuel cost is rupees 5,000 per MMBTU, million metric BTU, okay, and total operational hours as 8,000. The reactor heat load is 2.58 million BTU that we just determined. However, the heat that needs to be generated at the furnace will be this divided by 0.6 into 0.8, because 20% will be lost. So, this divided by 0.8 into 8,000. So, the total heat that needs to be generated, okay, or this I will heat generated in the furnace will be 5.375 million BTU into 8,000 this many BTU per hour into 8000 hour per year. So, the annual heat will be 43,000 MMBTU, and then the fuel cost will be 43,000 MMBTU into 5,000 that will be 215 million or rupees 21.5 crore. So, this is how we have solved the problem of flow sheet synthesis for the IPA process. These are obviously very preliminary calculations. In the subsequent lecture, we shall see more detailed calculations, especially the calculations of distillation column and the feed to effluent heat exchanger, all those things.